Hello guys, how is it going? It's me, it's my earbuds. Please confirm if you can hear me out so that we start instantly. Let me also mention in Telegram, I don't know if Oran is here or not. Let me mention in Telegram that we have started the first session. Okay guys, let me give you some quick intro about this sessions that we have in this bootcamp for Salam Oran. Hi. Let me give you some quick intro about what we're gonna go through in this sessions. Well, we are gonna talk about centroid decomposition and solve problems from centroid decomposition. We are gonna go very fast, like the previous boot camps, because we wanna really get the best value of the time. Okay, no worries. Hi, good to see you too. So, yeah, we're gonna go over everything one by one, and we're gonna go over them very fast. In the first session, first we're gonna let me zoom in so that it doesn't mirror. In the first session, we're gonna talk about what Centroid is and solve our first problem from Centroid and its proofs. And there are a lot of beautiful things that is there. Can you make a course on C++? I don't know if you've seen the roadmaps that we have. Definitely, guys, try to first of all make sure that you're in roadmaps. And as you see, there are so many roadmaps that are hidden at the moment, but they are basically they're gonna be released very soon. If I open an incognito tab, you can see it here. We have right now this Centroid, which is exactly the course that we are going on right now. I mean, we're gonna go over this Centroid one, and then we have other than this, we have this combinatoric C++ intro and dynamic programming intro. All of them are prepared very recently. And I think that they have the best quality for you to learn. I mean, the goal was to create something that does not exist, something that is actually amazing. You know that it's always our standards to try to do something amazing, something that doesn't exist at the moment. Yes, many people preferred Centroid, and it's the vote of the most of the people. So whatever most of the people say, we're going to go on that. So, shall we start? I mean, without losing any more time. As I said, as I promised, we want to take the best use of your time. So, I think we should start quickly and going over the topics. And guys, I recommend to you that at the same time that you are, let me open user view in here. At the same time that you are listening to me, open this centroid decomposition roadmap as well. We're going to go over it actually. So this way you can read each part as well. I think that's also something that is going to help you a lot to learn it better. That's a very good thing that you can have. Any pre-requirements? No. If you know segment tree, why do I say segment? Sorry. If you know trees and graphs, then you will understand everything that I say. Not segment tree. I don't know why I said that. So let's start talking about it. You just need to know that what trees are, what graphs are, and what DFS is. That's the minimum requirement for understanding what we are saying. Okay, let's start, guys. First, Well, guys, the first thing is that we know about trees and we know about graphs and we know already we can solve some problems. The problems that we face in Centroids, usually, there are problems like, for example, how many paths have length k? Or what is the closest red node to some node u? I mean, these are just, we want to give an intuition of what the problem is. I mean, maybe precisely they will be a bit different. Sometimes we cannot check all the paths and go over everything. If we do that, it's going to be too slow. So that's why something like Centroid is super important. Centroid, all it does is to make the time complexity way better. And for the problems that n is large, n is up to 10 to the fifth or 10 to the sixth, it will make it faster so that it can fit the time limits. So first, let's define the centroids. Guys, centroids, like, let me first take in here. Like an array, you know binary search. You know how binary search works. Similar to array and how binary search works, each time you pick the middle one and it will go on one of the ways. Centroid is kind of similar to having a binary search on the tree. Centroid is gonna be the middle point of a tree. So like when in an array, we have a middle point, we want to somehow define a middle point for a tree as well. And now, how do you think we can define the middle point of the tree? You tell me. Maybe you have heard it before, or maybe you have some intuition. What do you think is a good definition for the middle point of a tree? Middle points. Tell me about your ideas. What is the definition? Or if you have heard it before or anything, tell me, what do you think? Middle of diameter, center of the tree, middle level. Well, middle of the diameter is not a bad idea. And it's called center. So these two are the same thing. Middle of the diameter is called center, that we will talk about it as well, which is different compared to centers. What centered is? The question is what centered is. Sum of its distances from all points is mean. That's a very good way to look at it. Yeah, that's a very good way of looking at it. But we should see that, okay, why? I mean, why is it like that? Is each subchild nodes have less than n half? Exactly, yes. That is the definition that we are looking for. Centroid is a vertex that if you remove it from a tree, each subtree will have at most n half vertices. That's the definition of a centroid. Similar to how in an array, if you remove these middle elements, both sides are gonna have at most n half elements, right? In the similar way, we are defining it for a tree. We say that the middle point of the tree, we call it the middle point, but it's actually called centroids. Is a vertex that if we remove it, each component will have at most n half vertices. And we see that why is it so useful and helpful. In binary search, we saw that, for example, each time we pick the middle one and we search either in larger places or in smaller places. Each time we go to n half. In here, in Centroid, you get a similar thing. I mean, when you remove it, you know that each of the possible connected components, have n half vertices, which is a very good thing. So this vertex is called a centroid. And the centroid, as I wrote here, is a vertex that if we remove, each of the subtrees that will remain will have the size at most n half. For example, if it's a path, the centroid is gonna be the middle node. Or in a star graph, the centroid is gonna be this vertex. In a star graph, star, you know that is a vertex that is connected to all the other vertices. The centroid is this one. So this is the definition of the centroid, and I talked about how it's similar to arrays. And now we want to say that. Now the question is that, that's great to hear. That's great to hear. Yeah. So now the question is that, does every tree have a centroid? I mean, what if a tree did not have a centroid? Why should a tree have such a vertex that if we remove it, each subtree will have at most n half vertices? So now we say that each tree, we want to show that each tree actually has a centroid. Each tree has a centroid. So this special vertex that we defined, that we said that there is a vertex that if we remove it, each connected component will have at most n half vertices. We want to say that each tree has that actually. How? We actually prove it by finding it. We prove it by finding it. I mean, I want to prove that something exists, then I will find it and show it to you. Then I have proven that it exists, right? So we actually want to do the hard part. We say that not only we will prove that, but we will find that as well. So if I find that and I can show it to you, then you will agree that, okay, it exists. I found it for you. So the way that I will prove that a centroid exists is that I will try to find it and I will say that, okay, this vertex is a centroid. Any tree that you can give it to me, I can find the centroid in it and give it to you. So centroid always exists. Okay. What is the idea to find the centroid? The idea that we have to find the centroid is going to be like this. We start from any node in the tree, start from any node like V in the tree. So we start from a node like V. Either it is centroid or it is not centroid. If it is not centroid, if it is centroid, that's good. I mean, if I found the centroid, I give it to you. Otherwise, it means that there will be one connected component that its size is greater than n half. And definitely there will be only one because we have n vertices in total. So it is not possible that another one is also greater than n half because then we will have more than n vertices. So all the other components should have now less than n half when one of them has more than n half. So our greedy approach would be like this. I mean, when we start from V and we see that one side we have more than n half vertices, we simply go that way. We go to that node. Let's call it U. And then we will check U. And we are sure that from U, we will not come back to V because all the vertices in here have at most n half vertices. When in the left side, we have more than n half vertices. In the right side, we have less than n half vertices. So then we go to U and then we try the same for U. Again, for U, either it's a centroid or it is not a centroid. If it is not a centroid, again, we can say that there will be one place, one direction that has more than n half vertices. Then again, I can go to that. I can keep continuing doing this as long as there is a vertex that its subtree is greater than n half. We will go that way. And by doing that, at some point we will stop. Yeah, bootcamps are the sessions that we have, and the roadmaps are actually the topics that we're going to go on. I mean, they are written. I mean, you can open the roadmaps here. Roadmaps have all the information that's needed. Yes, so now the question is that how do you calculate that how many vertices are in that site? Yeah. That's another way of saying this. There are actually, I want to, in this session, I will give you 3 proofs for existence of centroids. And each of them has their own beauty. So, I mean, we have a lot of interesting things to say. So, first, I'm just talking about this one. And I'm saying that I start from a vertex, and each time, as long as it's not a centroid, I know that one of the neighbors has size greater than n half. So I will go to that neighbor. I will keep doing that until I stop. At some point, I will stop because I cannot do it infinitely. I know that I don't have infinite number of vertices. So at some point, I should stop. And that vertex is a centroid because it's the place that I stopped. It had no neighbors that its size was greater than n half. So the greedy approach was very simple. Just start from a random node. If it was centroid, it's good. If one direction, if one side had more than n half vertices, just go that way. And keep doing it. At some point, you will stop. You won't have any neighbor that its size is greater than n half. And that's going to be your centroid. Okay, this is just the theoretical proof of that centroid exists. I will also talk about how many centroids you might have. I will also talk about that in this session. So that's actually what we do. Is it clear so far? I mean, is the theoretical, hey, hi. Is the theoretical part clear? If it's clear, please put a plus or use this emoji, this 100 emoji. So the approach, I mean, now we've proved that a centroid exists. We said that we start from some vertex. As long as it is not the centroid, we will keep going to the direction that has more than n half vertices, and at some point we stop and that's the centroid. Awesome, awesome. Yeah, this works if there is no cycles, and because it's a tree, there are no cycles. That's why you say it's a tree. So yes, I mean there are no cycles. It's working if there are no cycles. Now let's talk about its implementation. How do we implement this? Well, implementation, guys, usually what we do. So first, let's finish this. So each time we are going to a neighbor with a larger size, at some point we will stop, and that is your centroid. So that's all about this unit. Now, next, we will talk about how to implement it. We talked theoretically about it. Now, how to implement it. For implementation, I usually make my tree rooted from some vertex. Like vertex, let's say vertex 1. I make my tree rooted from vertex 1. And then, you know that's what's making a tree rooted mean from DFS and I mean the things that we have said about trees. So I make the tree rooted from some vertex, and I will try to calculate for each vertex what is the size of its subtree. I will calculate for each vertex that what is the size of its subtree. And it is very simple. We can just do a DFS. I mean, I define an array SZ, and SC, for calculating SC of V, I can just do a DFS and call the children of V. And then SC of V is going to be the sum of SC of its children plus 1. SC of each vertex, I mean here, for example, V is the child of, vertices V are children of U. So SC of U is going to be 1 plus sigma of SC of V. So actually, each time, for each vertex, we will call the DFS of the children. First, for example, this one calls the DFS of this one calls this one. The size of this one is 1. It's a leaf, is 1. The size of this one is 1, this one is 1. This one is going to be the sum of its children plus 1. So it's going to be 1 plus 1 plus 1 is 3. This is 1. This is the sum of its children plus 1. 1 plus 3 plus 1 plus 1. 1 plus, yeah. And this one is 1, this one is 1, this one will turn into 3, this one is 1, this one is 1, this one is 1, this will be 4, this will be 5, and this will be 15. So this is how I can calculate how many vertices exist in the subtree of each vertex. It's a DP solution. I can just easily calculate DFS of the child. For each vertex u, I will call DFS of the child u, and I say that SC of v plus equal to SC of u. That's it. And at the beginning, you can choose SC of v to be 1 at the beginning, because at the beginning, only v itself is in its own subtree. And then when you call each of the children, you will add the size of those. So now you have a rooted tree with the size of the subtrees. Now it's going to be very simple for us to find the centroids. It's very easy. Not that much. I mean, we're on this roadmap, so I mean, you can maybe see the things that we said. Maybe even if you listen from now, you will understand everything. Because now we are talking only about how to find the centroids, which is also the proof of existence of centroids. So now that we have these sizes of subtrees, I mean, this is, guys, very famous and important thing in trees. That's the thing that you should definitely know. Now we can now find the centroids. How? We will start, I mean, after calculating the size of the subtrees, we will start from the roots. And we look at the children of the roots. If one of them had size greater than n half, we will go to that. In here, none of them has size greater than n half. But if we had, for example, more vertices here, then we would go here. So what we do is that we start from the roots and we look at the children of the roots. If one of the children had size greater than n half, first of all, we know that only one child can have size greater than n half. This is a key. I mean, this is a key point in centroid. That helps us a lot to find the centroid. The point is that there will be only one that its size is greater than n half. We will go to that one, and then from that one, again, we will check its children. If the size of the subtree of 1 was greater than n half, we will again go to that one. At some point, we will stop, because the height of the tree is limited. Consider the vertex that we stopped at. I mean, assume that this is the vertex that we stopped at. We know that for this vertex, we know that the size of all its children are at most n half. Why? Because I didn't go to any of its children. If one of them had size greater than n half, I would go to that. Also, the size of the subtree that is outside is also at most n half as well. Why? Because this subtree was greater than n half that I came to it. The size of the subtree of this vertex V, or let's call it C, was greater than n half that I came to it in the first place. Therefore, the number of vertices outside of it is not greater than n half, is less than n half. Also, all its children are less than or equal to n half. So this vertex is actually the centroid. So the implementation would be like this. We will start from, I mean, we want to get the centroid. We will have a node, and we know that what is its parent and the total nodes. And I say that total nodes is actually n. I say that I will go over all the neighbors. I say that if a neighbor is not equal to parent and I have not visited it yet, and if size of the neighbor is greater than, total nodes greater than 2, you will go and get centroids inside that subtree, and you will return that. If at the end none of them were like that, you will return this node itself. So that's how the function of getCentroid works. You call the root, and starting from the root, if one of the children had size greater than n half, you will call getCentroid in that subtree, and you will return the output of that. Otherwise, you will return this node itself. Okay? Why do we have this visited? For now, this visited is not that important, but we see in the future that's why it is important. Because sometimes when we are working with centrals, we remove, we delete, we kill actually some of the nodes that we will see it in the very soon. But for now, it's not that important. Is it completely clear? If it's completely clear, please put a plus or use this emoji. What is this topic useful for? It's useful to solve many tree and graph problems. Centroid is an important uh, algorithm, is an important topic that helps you solve a lot of problems. Centroid is more frequent than HLD. Anyway, I'm preparing the roadmaps for all of them as well. I mean, HLD is a bit different, but it has some similarities as well. I mean, guys, I have many good surprises for you as well. I mean, as you can see, I'm preparing, for example, heavy light as well. I mean, I will share it with you soon. There's some surprise. Some people, some people are shocked by the solution. Okay, so if it's completely clear, sure. If it's completely clear, let me know to move on to the next thing. If you had any questions, you can let me know as well. That's very funny. Okay, so this is how the centroid will be found, right? I mean, we just talked about what centroid is and how to find it. That was all that we have talked about. Yeah, we'll talk about it. I mean, we are gonna have roadmap for that as well. Let's get back to the implementation. We found out that how we can find that where the centroid is. Okay. Now, the next thing that we want to talk about is something called centroid tree, which is very helpful as well. And we're going to instantly solve a problem with it so that you instantly see that when it is useful. What is a centroid tree? It's a bit more advanced. It says like, I mean, I just give you a brief, and in the next problem, you see exactly what is that. A centroid tree is something like this. I mean, you have a tree, and then you will find the centroid of it. As soon as the centroid is here, for example, you will find the centroid, and then you have many components. You will call this, you will put this centroid as your root somewhere else. And then in each of these subtrees, recursively, you will find its centroid again. So assume that this vertex was A, then this vertex was B, C, and D. Then you will make B and C and D the children of A. And then again, you're gonna have several components in each of these. Again, in each of them, you will find the centroid. For example, assume that this is E, the centroid of this one, this is F, and this is G. Then you will put E and F and G as the children of B. And you will go so on. So you will find the centroid. You're going to have several components recursively in each one of them. Each one of them are a tree by themselves, right? I mean, if you just take a look at this place, it is a tree by itself. Then in this tree, you can recursively find its centroid. And then you will put this centroid, the child of this node. And then from that, if you remove it again, you have several subtrees. Then in each of them, you will find centroid, and so on. You will move on like this. This is called the centroid tree, right? It is kind of, yeah, like divide and conquer. Centroid in general is something like divide and conquer. Centroid is something in a tree. It's a concept for trees. Guys, is it clear fully? We will talk about how much it would take or anything. I'm just talking about the definitions so far. I'm saying that the centroid is something like this. If it's clear, please again put a plus or use this emoji. It's also a geometry term. Yeah, I mean, that's something different. We are now defining it in a tree. Hi. So that's actually how Centroid's tree is defined. Now, let's talk about a little bit about this Centroid tree. What you can say about Centroid tree? What facts exist about it? So if we consider this Centroid tree that we built, can we say any facts about it? For example, what can be the height of this Centroid tree? And you know what height is, right? I mean, the height is the maximum distance from the roots to one of the leaves. Then what do you think is the height of this Centroid tree? Yeah, we changed. I mean, because now we have a community. I mean, we built this Repovive community, and now this YouTube channel is also part of this community. And we have now way more than just videos. We have these roadmaps and many things. Yeah, actually, we can give an upper bound of log n. Why? Because, guys, in here, we said that when we pick the centroids, each of these components have size n half. So do you agree that when this has size at most n half, when we pick the centroids here, then each of these will have the size at most n fourth? Because the size of the components in here was at most n half, and when we choose B as the centroid, then each of the components can be at most the half of that n half. So each of them will be n fourth at most. So actually, if the size of this component is n is less than or equal to n. Each of these are less than or equal to n half the size of the component that they were the centroid of. And then each of these will be at most n fourth their components. And you can easily see that the components of their children will be at most n eighth because their component is n half, and when they are the centroid, each of them will be the half of the previous one. The point is that each time that we go down, it should divide by 2. And that's the main point of centroid. That's the main point of centroid. That's the main point why division by 2 is so powerful. Each time it's being divided by 2. So the height of this centroid tree is of log n. As I wrote it here as well, you can see that each time the size drops by half as we go down. It starts from n, goes to n half, to n fourth, and so on. So the height of centroid tree will be of log n. And this is exactly the magic. And you will see that how it will be useful. Yes, actually, after converting, it's like a balance tree. Exactly. If it's clear, again, please put a plus or use this emoji so that we go to the next one. Worst case, we get to, yes, exactly. Exactly. If it is clear, we'll move on to the next unit. Okay. I guess that there are no other questions. Awesome. So now we will move to the next one. This is the first problem that we want to discuss. Ciel the commander. Let me bring this problem as well on Codeforces. Codeforces. So this is the problem. Let me send you the link. The link is on the roadmap as well. So let's see what this problem says. This problem says that we have a tree and we want to give a rank to each of the nodes. It's basically n. It says that we have n cities and n minus one undirected roads, and we want to give a rank from A to Z to each of the nodes. A is the topmost and Z is the bottommost. And the point is that if two cities, X and Y, have the same rank, then on the simple path between X and Y, there must be a city Z that has a higher rank. So we have to put characters on the vertices of this tree such that if two vertices have the same rank, some vertex in the middle has a higher rank, a character with a higher position. You have to either do this for all the vertices or say that it is impossible. For example, let me tell you an example so that it would be easier to understand. For example, assume that this is the tree. I can, for example, put A here and then B here and B here and C here and C here and C here. You can see that if I do this, then between each two vertices that they have the same rank, for example, these two vertices have the same rank, these two C's. You can see that in the path between them, there will be at least one vertex with a higher rank. In this case, we have two vertices, but even one was enough. For example, this A has a higher rank than these two C's. So for each two vertices, if they have the same rank in the path between them, there should be a vertex with a higher rank. Is this? I hope that the statement is clear. If the statement is not clear, let me know. So this is the problem that we wanna solve. Okay. So we actually, for any two nodes with the same rank, the simple path between them must have a node with a higher rank. I wrote it vice versa. I mean, if U and V are B or C, there must be an A on the path. I will fix it. But the problem at the end would be the same. I mean, because it just is symmetric. It just reverses the order. Yeah, we will talk. We will talk if it can be impossible or not. So now we will solve this. We will see that what can we do. And thank you guys. Guys, in order to do this, what I do will be this. Remember that centroid tree that we had, that we just talked about. Remember that centroid tree had height log n. What happens that in that centroid tree, I will talk about that. We will reach to all these guys. Can I start the tree and label the nodes that we have to label the vertices that we have right now. I'm saying that consider the central tree. Basically, what we do is this. Let me say it, go through it this way. Consider that this is our tree, is something, and this is our centroid. I will put an A in my centroid, which is a higher rank than anyone else. And then I'm gonna have several subtrees. In each of these subtrees now, I will use letters from B to Z to solve them. I mean, now I start from B and I solve them. Starting from B, I should pick characters that are at least B. Then if I do this, if I never use A again in any of them, and I will put A here in the middle, if I recursively solve this correctly, and each pass in each of them are correct, each pass between two of them is correct as well, because these two vertices cannot have A. They are definitely something greater than A. And in the pass between them, there is an A. So definitely there is something with a higher rank between them. And again, what I do is that next time in each of these subtrees, I will choose the centroid and I will put a B in there this time. And then I will have a next layer again that We have several subtrees here. In each of them, again, I will start from C now. So actually, if we take a look back to the centroid tree that we have, on the root of the centroid tree, I will put A. On all the children of that root, I will put B. On all the children of that, I will put C. On all the children of that, I will put D, and so on. If I do this, I'm sure that in the past, between each two vertices with the same character, there is one vertex with a character with a higher rank. Why? Because I prove it by induction. I say that, okay, I have A here. It's kind of like divide and conquer. It's a centroid. It's basically divide and conquer on a tree. I say that divide it and solve each of these recursively, assume that each of them are correct. If each of them are correct, then the combined thing is correct as well, because we have put an A in the middle, which is more valuable than anything, is a higher rank than anything. So if I choose two nodes from different subtrees, definitely there will be something between them that has a higher rank. And that's all. That's all we do on this problem. Yes, I will show the code as well. Yeah. Is it clear? And yeah, it shows that it is never impossible. It's always possible. Yeah, and because log of n, if log of n was bigger than 26, then it was possible that it would be impossible. But now, because log of n is less than 26, it would be always possible. The DP roadmap is locked. How come? Let me open it in incognito tab. Roadmap. It's not locked. What do you mean? This roadmap is locked? You should have access to it. Can you check it out? If there's any issue with it, let me know. I will fix it after the after our session. So guys, is the solution completely clear? I will now move on to the implementation. If the solution, theoretically, solution is completely clear, I will go to the implementation now. Is it clear? You have to do it task by task. What do you mean? I don't understand. Oh, okay. You are talking about the guy who says it's unlocked. Yes, it's task by task, guys. When you do the task of that unit, then the next unit unlocks for you. No. Basically, the solution that we have for this problem is this, but there are different solutions for centroids itself that we will talk about that. Isn't it important to say the LCA of U and V in the centroids tree belongs to the... Yeah, basically, that's actually what we showed. This induction actually was showing that. This induction was actually showing that. We say what is in your mind in another way. We said that assume that inductively, assume that these are okay. Then A that connect these things makes the paths that are between them okay as well. But yeah, we could also say that in general, in the centroid tree, the LCA of each two nodes in the centroid tree is definitely in the path between them. Why? Because this vertex was a centroid at some points, and in that point, it disconnected these two parts. Therefore, it's definitely in the path between them. In general, guys, in a centroid tree, the LCA of each two vertices is definitely in their path. Why? Because that vertex was a centroid at some points. Consider the points where this vertex, like V, was the centroid. In that point, it definitely has separated A and B. A was in one component and B was in another component in that point. Therefore, V is definitely in the path from A to B. Okay. So that's also something that we should say. Yeah. Yeah. Great. Uh, there might be a solution without centroids for this problem as well. But the main thing that we wanted to talk about it on this problem was the centroid thing. I mean, that's what we want to learn in this section. So now let's talk about the implementation of it. Let's see that how we implement it. Oh my God, it's funny. I accepted this problem 10 years ago or something, but I actually accepted it on December 10, 2023 as well, which was for the first video that I made on YouTube. That was censored. I explain it in there too. I mean, if you open it, I mean, you can see that video. That's that was the first video ever that I made for this channel. This where I talked about censored. I implemented this at that time. That's nostalgia. So what do we say? I mean, we actually say that we define main, and inside that we solve 0 and A. 0 is the root of the subtree that we are at, and A is the current character that we are on. What do we do? First of all, guys, this is the important part. This is the part that you should be very cautious about. That's how to implement this thing. Now we are actually implementing Centroid 3. So, as you know, we just said that in our solution, we just each time pick the centroids, and then we will go to the different subtrees and choose the next character in that one for the centroid of that one. First, guys, we know that we can have a subtree size helper. That is a DFS that will go over all the vertices, and it will calculate the sizes. Size of u will be 1 initially, and then for all the children, size of u plus equal to size of v. That's what calculates the size of the subtrees. And then we have a find centroid helper. That was what we already talked about. And then the full implementation would be something like this. We will, at the beginning, find the centroid. I mean, we have a function named decompose. First, we will calculate the sizes. Okay, we will calculate the sizes, and the total nodes is going to be the size of the root. Then we will call the find centroid thing that we have, and then we will assign rank to it. The current char will be assigned to this centroid, and then we will remove this centroid. Remember this visited that I told you that for now it's not that important? And we add it in here that we go to a vertex if v is not equal to par and it is not visited. I prefer to choose the dead, the name to be dead, because it gives a better intuition. We are killing that node now. We say that, okay, we assign this to here, to this vertex, and now I kill that node. And then I will have a for on all of its neighbors. If they are not visited yet, I will run the same decompose function from one of the vertices in there. I mean, we can only just call that neighbor and that rank char plus 1. I'm actually calling, I call a subtree by one of its vertices. First, I'm just finding the centroid, and once I found the centroid, I will call this subtree by just passing one of its vertices. If I just pass one of the vertices of a connected component, then by DFS I will find the rest as well. And because I killed this node, these DFSs will not intersect with each other. This DFS only will go over these vertices. This DFS will go over only these vertices. This DFS will go over only these vertices. So if we get back to my implementation, I kill this centroid after setting its value, and then I will have a for on all of its neighbors. If one of the neighbor, for each of the neighbors, if it's not dead, it means that there's a component there. So I should call that solve of u and current char plus 1. This is the subtree size helper that will calculate the size of the DFSs. And this is the find centroid function that we have. Each time we say that if u is not equal to pair and u is not dead and 2 times size of u was greater than the total number of nodes. We will go to that part. So this is how centroid tree will be calculated. So we will see that what is the centroid, and we remove that. And each time when we want to solve a subtree, we will just pass one of its vertices. That's the main idea. Yeah, we're almost 2 years now. Centroid, yes, is kind of an advanced topic. Yeah. DP roadmap is not locked, guys. The point is that it's a roadmap. So you have to see, I mean, this is locked as long as I have not done this. When I do this, you have to also say that I have accepted it as well. I mean, if you don't accept it, you get just two stars. But if you click on this as well, you get the full 3 stars. So when you do one, the next one will be unlocked. Yeah. It's a roadmap. It's not a doc. We didn't try to create a doc. We tried to, guys, the roadmaps are for the reason that they will go with you step by step. You can see that. I mean, and it takes so much time to prepare each of these roadmaps. I mean, it's way harder than I asked because I want to design it in a way that it's like I'm teaching someone and we want to go over topics, advanced topic with each other step by step, small step by small step. You see that in each part, I try to give some intuition and I invite you to think about going to the next unit many times. I say like, I give you sometimes hints and I say that now think about it before going to the next topic, etc. So it's, I did not design it to be something like docs that you can find on the internet. It's actually something that goes with you step by step. And that's how I think that it's going to be useful. And when I make all of the roadmaps or all the topics, then I'm going to create a total roadmap of competitive programming or ICPC, different things as well. That for each one of them, which ones of these roadmaps you should study and in which order. So then you have the clear, then you know the clear way of how you should go forward. Okay, guys, is this implementation of this problem completely clear? If it is, please put a plus or use the emoji. This. Lazy segment tree is more frequent. Maybe. They're almost not much different. Yes, segment tree in general is more frequent, but lazy, I don't know. Around the same. Did you delete some problems in the problem section or you didn't notice? The problems must be back. The problems were deleted by mistake, but we restored it from our backup. Are some problems not there anymore after the backup? Anyway, guys, I'm gonna add new problems in here very soon. So if you are looking for the problems, I mean, we have 3 sections, beginner, intermediate, and advanced sections that I add problems, the best problems that exist from different tags. These problems are tag free. If you want to go tag by tag and topic by topic, you should go to this roadmap section. But these are tag free problems that are the best problems of each topic. You can go there and I'm gonna add more problems to there. And guys, if there's something else that makes Repovive more amazing, definitely let me know. I mean, our goal is to make something really, really amazing and find all the pain points and resolve them. So let me know if there's anything that you think would be great for you to be added. For now, no. Maybe at some point if you vote. And guys, also we have this teams section as well. And I see that there are many new teams added. That is also very helpful for you. If you are newbie, for example, like I invite you to join this rich pupil team that is made by one of you. 92 members are already there. There's one rich candidate master. You can also create your own team as well and let others join your team. This helps you find like-minded people who are trying to learn things that you are trying to learn. So if you are not in a school that people are studying competitive programming, I know that it's really hard and it makes people suffer. So I made this section so that it resolves that. So you can go in here and find like-minded people around the level you are looking for, and you can actually push each other to grow. Yes, I mean I'm preparing all the roadmaps, and I will create based on these roadmaps. There will be a higher level on them, a roadmap that's each of its units is a roadmap now. You know, so there will be an upper level that's will be an ICBC roadmap or a competitive program roadmap or an IOI roadmap. They are a bit different. So I will prepare them. Oh, that's a lot, 9 months. For now, it's just after that you will get the Discord link of these, and then you can meet people there in the Discord, and then talk to people and get familiar to the people. Okay, so let's, if everything is okay, let's move on to the next problem. Yeah, maybe we should explain this more. It's actually for you to, I mean, find the contacts of other people who are similar. So you find them in Discord this way. You will be added to the group in Discord, and you can find people there. Some of the teams are open to everyone. Some of them are request based. And when you create the team, it would be the same thing. You can either leave it open to everyone. Everyone can instantly join or request. There's also one team that are for people who want to build and learn with Repovive. If you are interested in contributing to Repovive and learning this process, we are people who all with each other try to learn many things. If you want to be a part of it, we have a level 0 that you will get some tasks. And then if you do well, you can go to the next level and the next level and the next level. And maybe at some point you will become a core member of Repovive if you perform well in the tasks that you have. I see that 2 new people have join requests now, so it will add up to 107 members so far. We are trying to find a good way to manage this level 0 as well, because that's a huge part of Repovive. Okay, so let's move on to the next thing now. I guess that implementation of this was clear. Now we get to very interesting parts, very beautiful and interesting parts. I want to give another definition of centroids. Guys, so far about centroid, we said that centroid is a vertex that if we remove it, each connected component will have at most n half vertices. So centroid is a vertex that if we remove it, each connected component will have at most n half vertices, right? The next thing that I want to say is that I want you now, this time, to consider the vertex that its sum of distances to all the other vertices is minimum. So for each vertex, calculate the sum of the distances for each vertex, like V, define D of V as the sum of each vertex U, distance of V and U. And distance is the number of edges between them. Now, consider the vertex with minimum value of D. Consider the vertex with minimum value of D of V. The V that minimizes this. Then I say that this vertex, I want to talk about the relationship of this vertex and centroid. And my argument is that this vertex actually is the centroid. So another definition for centroid is the vertex that the sum of its distances to all other vertices is minimized. Centroid is a vertex that if we calculate the sum of distances from centroid to all the other vertices, this sum is minimized. And now we will talk about why. So if I define S of V as the sum of distance of V and U, the sum, so it's the sum of distances to all other vertices. I want to say that this is gonna be, I mean, the one that it minimizes this is gonna be the centroid. Or in other words, we have to show that if C is centroid, then S of C is minimal among all the vertices. Then we have to show that also if S of C is minimal, that vertex C is centroid. First, let's just say that if C is a centroid, then S of C is minimal among all the vertices. So first, I say that, assume that, okay, I have a vertex like here, assume that it's not a centroid. And S of this vertex V is minimized. If it's not a centroid, it definitely has a component next to it that it has more than n half vertices. I say that it's not possible that S of V is minimized. Because if instead of V, I go to this vertex, let's call it U, then I know that I get closer to all these vertices by one, and I get farther from all these vertices by one. And because the number of vertices that I get closer to is greater than n half, then definitely my total sum of distances will decrease. So let me repeat. Assume that I have a vertex V and it's not a centroid and S of V is minimized. I said that it's a contradiction because if it's not a centroid, there's a component that has more than n half vertices. And the rest of vertices, I mean, these are less than n half and more than n half vertices. Let's call it U. Then I say that the sum of distances from U to all the other vertices is better than the sum of distances from V to all the other vertices. Why? Because if instead of V I come to U, then I get closer to more than n half vertices. Let's get, say, A. Let's say there are A vertices here and B vertices here. I say that S of U is gonna be S of V minus A, because to all those A vertices, I'm closer by one. Plus B, because to all the other B vertices, I'm farther by one. And because A is greater than B, S of U is greater than S of V, which is a contradiction. So it's not possible that some vertex, the vertex that is that has the minimal sum is not the centroid. That's impossible. That's impossible that the vertex that has the minimum S of V is not centroid. Is it clear? Thanks. Thank you so much. With that, it's the only one. Thanks. So, is this clear? So, the vertex that has the minimum value of S is gonna be definitely the centroid. It's not possible that it is not centroid, because if it's not centroid, if so, that's actually a very beautiful proof for existence of centroid. I say that let's consider the vertex that the sum of its distances to all the vertices is minimized. Then all of the, if I remove it, all of the components should have size at most n half. Because if one of them had size greater than n half, by just choosing the vertex in that way instead of this one, my S would decrease. So that would be a contradiction. That's a proof for existence of centroid, because anyway, at the end, these SIs have some values. One of them is minimum, at least. And that minimum is definitely a centroid. In other words, to minimize the S of U, you need to keep moving this. Yeah, exactly. To minimize S of U, you need to keep moving to the subtree with size greater than n. So now this gives us another solution to find the centroid as well. I mean, I wrote the proof in detail here. And then I say that I can use this to find the centroids. How can I do that? I can use a simple rerouting idea. I can calculate the sum of the distances from roots. It's very easy. I do a DFS, I'll keep the height of each vertex. And the sum of the heights is going to be the S of the roots. It's going to be S of 1. And then I just talked with you about how S of a vertex V can be calculated from S of its parents. S of V is going to be equal to S of parent. This idea is called rerouting. We first calculate the answer for the roots, and then we keep rerouting. We say that, okay, assume that if the root was P, the answer was this. Now, if the root is V, what is the answer? I say that it's the same if the root was P, but now we are closer to these vertices in the subtree of V, so minus SV of V. But we are also farther from these vertices that are outside of the subtree of V. So plus n minus SC of V. So actually S of V is gonna be S of P plus n minus 2 times SC of V. And that's all. And this way, I can, for each vertex, now I have S of 1. Using S of 1, I can calculate S of the children of 1. And using the S of the children of 1, I can find the S of the children of that, and so on. So S of each vertex will be calculated, which is the sum of the distances from that vertex to all the other vertices. And this way, at the end, I can see that which one is minimum, and I can report that is the centroid. Is it clear? If it's clear, please put a plus or use this emoji. So that's the next important thing. Awesome. 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 Great. So that was the second way to find the centroid. Now, there is more that we should say about it. And now we're going to more go into that. Repeat the formula. Yeah. I say that if this is S of P, S of V is going to be equal to S of P minus SC of V, because now we are closer by 1 to each vertex in this subtree. So minus SC of V. And now we are farther by 1 vertex from all vertices here. So plus n minus SC of V. So this is how S of V will be calculated. It's S of P only to SC of V vertices. I'm closer now. To n minus SC of V vertices, I'm farther by 1 now. That's all. Okay. So that's how we can find out this values. It's me. But no, still, there's a lot of interesting things that we say. Next, I want to talk about how many centroids we have, and that helps us to do some more things as well. I want to now talk about how many centroids do we have. Okay. The first thing that I say is that assume that I have 2 centroids and a vertex is in the middle of them that is not a centroid. Or let's say this. This is the best way. Assume that I have 2 centroids and they are not connected by an edge. Okay? Assume that I have 2 centroids and they are not connected by an edge. I don't even care what is between them. So there's a centroid here. There's a centroid here, and there's a path to the other centroid. And there is at least 1 vertex in the middle. At least 1 vertex in the middle. What does it tell us? Because these vertices are centroids, consider the first vertex to the right of it. We know that in here, I'm going to have at most n half vertices, right? At most n half vertices. So what does it say? It says that if I consider this part, if I have a path here, and there will be some vertices from next to this part, I mean next to A, that are not on this path. Consider that whole subtree. This subtree should have at most n half, at least n half vertices. Because if I remove all of these, only the part of the subtree that is one of the neighbors of A remains, which should be at most n half. Okay, assume that A, this is the neighbor of A. This should have at most n half vertices. So this part has at least n half vertices. In the same way, for B, I can say that these parts will have at most n half vertices. Therefore, this part will have at least n half vertices. So now if you consider these green parts and these red parts, each of them have at least n half vertices. So the total number of vertices will be at least n half plus n half, plus there will be at least one vertex in here. We said that there is at least one vertex in here. That is not in this green subtree and it's not in this red subtree. And these two subtrees are disjoint. One of them, I mean, we had a path. This is one end, this is one end. We said that both of these ends are at least n half vertices. And we said that there is at least one vertex in the middle as well. You can see that then the number of vertices we have is going to be at most n, at least n plus 1. But at the same time, the number of vertices is n. So we have n greater than or equal to n plus 1, which is a contradiction. So it's not possible. So it's not possible to have two centroids that they are not neighbors of each other. Each two centroids that we have in a tree, they should be neighbors. Do you agree with it? And yes, that automatically shows that we cannot have more than two centroids. Exactly. We just proved that each two centroids should be adjacent. But at the same time, we cannot have three vertices that they are pairwise adjacent. Right? So, because otherwise we will have a cycle. So we will have at most two centroids. How do we use the information of S of U? S of U is one way to calculate the centroid, to find out which vertex is the centroid. So once you calculated S of U, then minimum of S of U, the vertex with minimum S of U is the centroid. So that's how it will be used. So now, guys, we said that each two centroids should be neighbors, but at the same time, we cannot have three vertices such that they are pairwise adjacent. So there will be at most two centroids. And now let's talk about these cases more in a better way. Assume that we have two centroids. Now I want to consider the case that we have two centroids. I want to see that, how does it look like? I have two centroids. They should be neighbors, as we said, and it means that there should be exactly n half vertices here and exactly n half vertices in here. That's the only way that we have two centroids. So the only way that we have two centroids is that we have an edge that on one side of this edge is exactly n half vertices, and in the other side we have exactly n half vertices. That's the only way that we have two centroids. There will be an edge that on one side of it we have n half vertices, and on the other side we have n half vertices as well. Otherwise, we will have only one centroid. So that's what we can say about the number of centroids that we have. Is it clear? Yes, arg is argument. Yeah, exactly. I can't edit it. But yeah, you're right. That's the more precise way of writing it. Is it clear, guys? If it's clear, again, please put the plus or use the emoji. Does there exist a centroid if edges are weighted in a tree? Uh, if edges are weighted, we just don't care about the weight of the edges. The centroid is defined on the unweighted tree. So we just ignore that. And again, there will be a vertex that if we remove it, each connected component will have at most n half vertices. So yeah. And even if it is weighted, again, we can say that the centroid is going to be a vertex that the sum of its distances to all the vertices is minimal. Yeah. I think even if it's weighted, I can say that there will be, even if it's weighted, assume that some vertex has minimum S of V. I say that it's a centroid. Why it's a centroid? Because again, assume that one connected component has more than n half vertices. If I go there, assume that this edge has weight W. Then I get closer by W to more than n half vertices, and I get farther by W to less than n half vertices. So still the args mean of S is going to be the centroid. Yeah, it's going to be the same. It's going to be the same. Exactly. Awesome. Guys, as you can understand, I was staying up to prepare these roadmaps. So yeah, I almost had very, very low sleep. So, okay. So if it's clear, let's move on to the next problem. I hope that today I can prepare some of the roadmaps and send it to you guys. Thank you. Yeah, I mean, yeah. Okay. I think now I should build a family. I should find someone who takes care of me because I don't take care of myself. I just take care of my work. That's the only thing that I care about. I don't care about anything else. Yeah. So let's move on to the next problem. So the next unit, I mean. So we showed that there will be at most two centroids, right? Now there's a very elegant proof as well for centroid that I want to talk about. This is a mind-blowing proof. And this was actually something that once when I was explaining centroids in a class, then I came up with this idea. I cannot call it my proof because, like many other things, it's possible that someone else has reached it as well. But that was something that I came up with that I will explain it to you. And it's a very interesting proof. Start gym. Gym takes a lot of time. I used to go to gym, but now I don't have time to go to gym, unfortunately. I don't have the luxury of going to gym now because of very tight time limit. So let's talk about this proof. This is the most interesting proof, in my opinion. Not just because I came up with it, but it really is. I say that let's consider for each edge, let's consider that there are two sides, right? Let's just direct it to the side with more sides. Okay. So we have a tree. For each edge, we will direct it to the side that has more sides. Then, and if they were equal, just randomly to any of the sides. If they were equal, just randomly to any of the sides directed. Then if you do this, we can say that how many edges do we have? We have n vertices, and how many edges do we have? Can you tell me? How many edges do we have? 1 hour is a lot, if you mean per day. Exactly, n minus 1. Like any other, it's a tree. So there's n minus 1. I wrote it very badly. So there are n vertices and n minus 1 edges. So there will be, each of these edges are the outgoing edge of one of the vertices. So do you agree that there will be a vertex such that it has no outgoing edge by pigeonhole principle? We say that there are n vertices and n minus 1 edges. So there will definitely be a vertex that has no outgoing edges. So all its edges are incoming. Do you agree with this? So I consider all the edges. For each edge, I will direct it to the side that has more vertices. If they were equal to any of the sides, I'm randomly, arbitrarily. Then I will say that because I have n vertices and n minus 1 edges, there will be. And each edge is the outgoing edge of one of the vertices. So the vertices in total have their outgoing degree in total is going to be n minus 1. So the outgoing degree of one of them is 0. And it means that for that vertex, all the edges are incoming. It has outgoing degree 0. So that's a centroid. Because none of these have size greater than n half. Each, if any of them had size n half, the direction was vice versa. So this is another proof that centroid exists. And we can also find centroid with it. We can just direct each edge and find centroid with it. This is also another proof that shows this. If it's clear, please again put a plus or use this emoji. Yeah, I honestly myself like this last proof more than anything else. I really enjoy. I also once wrote a post on Codeforces about it. Okay, awesome. Awesome. So we're done with this as well. Great. This concept was also similar to the CF question we did in class related to bipartite graph in the bootcamp, or okay. I hope that you enjoyed this first session. I don't remember which of the problems you mean, but maybe. Yeah, we solved many tree problems though. I hope that guys you enjoyed this first Centroid session. In the next session, now we built the structure on Centroid. You now know what Centroid is. You solve the problem from it. Make sure to accept it. Guys, join this in the bootcamp session. I mean, I see that only a few of you have joined this in the bootcamp session. In here, we have all the resources in here, the videos, the problems, and the discussion. If you had any questions, ask here. I will try to answer you ASAP. And problems will be added. Now the first problem will be added here, and the videos are here as well. So I will add you. I recommend you to go there, and I will add the problem there, and make sure to accept this problem. And now you know in 3 different ways you can prove that the centroid exists, and you can find it actually. And you know that how many centroids exist in a tree, and you know what centroid tree is. So we have all the fundamentals. From the next session, we're gonna solve more problems on centroids. And we're going to reach to advanced levels. To give a go to the Okay. You can send the link as well if you want. You can also put it in the discussion because I guess you can't send a link on YouTube. But in this discussion, you can comment it. If learning for loop is level 1 and level 0 is 100. Hmm. Centroid is gonna be 50, 60, 60 maybe. I mean, because at LGM level, it's not learning something, actually. It's problem solving. You don't learn new things, I think, for reaching LGM. For reaching LGM, I mean, from Grandmaster to LGM, I believe it's the ability of problem solving, increasing your ability to problem solve. Miss Colin too. Colin was in UMD. I mean, I think even in the last semester he was in UMD. I think now he's not. He graduated. So he's not here. Otherwise, I would ask him to come here. I'm right now in UMD. Otherwise, I would just ask him, I would call him right now to come here and say hi. We had many live streams and videos last year with Colin as well because we were teammates of ICPC too. Yes. Yeah. Great. We missed the long hair. I will invite him once. I will invite him once to be here. Good night to you guys. It's not night for us. It's 1:37 p.m. Guys, if you want to rate this live stream, how would you rate it from 0 to 10? Let me put a vote on Telegram channel. You can join in the Telegram channel, and the link of the Telegram channel is also here. No, it's Instagram. You can join our Instagram too, by the way. Our Instagram and Facebook and everything. This is the link of the Telegram channel. I should change the name of it from Algorithms with Cheyenne to Repovive as well. You can join there, and I will put a vote there. That's great. That these are all the good rankings. Right? That's good to hear. But definitely give us suggestion to make it even better. So it's not enough. We always want to make it better. Thank you. Thank you. So see you tomorrow uh, at 4 p.m. GMT this time, and we will continue working on these matters. That's great. That's great. I mean, I'm glad to hear. I hope that you will keep continuing growing, and I really hope that I can continue to help. I hope that we can do really, really amazing things on Repovive and help everyone. Let me know about anything that would actually help you and help Repovive get better. I will today hopefully add new problems to the problem section in Repovive, and I will try to launch these new roadmaps that we made. Some of them are on more advanced topics. I will do some more final touches on the Centroids roadmap as well. And I think that's it. I will add the problems to your roadmap as well. Okay, guys. So see you tomorrow. Bye.